The shortest path between 2 points might not be a straight line. It might be a tunnel, called through the very fabric of the universe itself. Wormholes have fascinated physicists and science fiction fans alike for a century now, promising shortcuts through space and time, from the heart of the Milky Way to distant galaxies or even other universes. Yet while they're among the most iconic ideas in modern physics, they're also among the most misunderstood. When we last explored wormholes here on SFIA in 2016, we discussed the many ways they might form and why most collapse before you could even send a photon through. Later in our Stargates episode, we imagined a civilization that could not only stabilize these cosmic bridges, but use them as the backbone of interstellar commerce and exploration. And we in turn explored some lesser-known wormhole theories and variations. Given that it's been a decade, I thought it was time to revisit that frontier and review the basics and answer common questions. We'll also be moving beyond to examine what it would really take to build and navigate an artificial wormhole network, a system enduring space-time tunnels we'll call stableways. Could such structures exist naturally? Could we create them ourselves? Would they allow travel faster than light or merely bend space to make the impossible routine? As we'll see, wormholes are not just convenient plot devices for science fiction. They are gateways into some of the deepest questions about relativity, quantum mechanics, and the ultimate fate of the cosmos. So let's open the portal and step through into the strange, beautiful world of Wormhole Stableways. What is a wormhole? A wormhole, at its simplest, is a tunnel connecting two distant points in space-time. They are not a portal you simply step to and emerge elsewhere instantly. That's a separate concept, and the one we discussed more in the Stargate episode. The name comes from it being that corridor or pathway, akin to a burrowed hole through an apple by a worm. And a key point to remember about them is they are not instantaneous for the traveler, taking seconds or minutes, and in the outside universe this can be much longer, ranging from about that time for the Morris Thorne wormhole to years, centuries, or even millennia for the Einstein-Rosen bridge and the Thorne-Ellis model. So shortcuts, but only relatively speaking. Alternatively, quantum scale or micro wormholes are thought to be effectively instantaneous, spooky action at a distance. In popular imagination, a wormhole mouth often is shown as a glowing ring or swirling vortex, but in physics it's better described as a kind of bridge, a topological shortcut through the four dimensions of reality. If space were a sheet of paper, folding it so two distant points touch, and then poking a hole through both to form a tunnel would give the basic idea. Though this is a handy way of visualizing it, it is not quite the same as actually folding space, which we also have an episode on. While the name wormhole came later, the notion first appeared in 1916 when Carl Schwarzschild described the solution to Einstein's new equations of general relativity that would later be recognized as a black hole. Amusingly, the idea of a star so massive not even light could escape it was actually a lot older. A few decades later, Einstein and Nathan Rosen revisited those equations and realized the same mathematics described a potential bridge between two regions of spacetime, now called an Einstein-Rosen bridge. Unfortunately, it was inherently unstable. The moment any matter or light tried to cross, it collapsed faster than the traveler could move. That's where things end, and I want to emphasize that for all of our exploration of wormholes, most physicists, myself included, assume that's probably it. The math allows them, but reality doesn't seem eager to cooperate. It wasn't until the late 20th century that physicists like Kip Thorne, Michael Morris, and Matt Visser explored ways to make such wormholes traversable, using forms of negative or exotic energy to keep the throat open. We'll talk about this more later today, but channel regulars know I'm very dubious about negative matter existing or being creatable, especially in the universe. I consider it more viable for traveling between universes or to hyperspace, over universes and underverses, which also have their own episodes. And don't forget to like and subscribe if you enjoy such content, and hit that notifications bell for alerts when more comes out. Anyway, shelving my skepticism for the rest of the episode, these later models replace the black hole's deadly singularity, which might not even exist, with a kind of space-time tunnel that could, at least in theory, allow safe passage between 2 points without violating relativity. Short form, you could create a shell of negative matter to surround the place the singularity would be, and it's operating opposite of normal matter and gravity, and thus stabilize a small sphere that is the mouth of the wormhole and would govern how big an object you could get through. In structure, a wormhole consists of two mouths, the entry and exit, and a connecting throat. In a true relativistic wormhole, those mouths would not be flat disks, but spheres hanging in space. Step toward one, and you wouldn't fall into it so much as through it, emerging light years away or perhaps in a different universe altogether. Modern theories even suggest wormholes might exist at quantum scales, constantly flickering in and out of existence in the foam of space-time itself. Whether these could be stabilized or scaled up to human size is one of the greatest open questions in physics. Could wormholes exist naturally? If wormholes can't be built easily, maybe nature does it for us. After all, the universe has had nearly 14 billion years to experiment with its own geometry, and we already know it produces stranger things than a science fiction writer could dream up. Black holes were once dismissed as absurd, neutron stars as impossible, and yet they sit all over the sky, calmly proving our imagination too timid. Moreover, the universe itself was probably a far stranger place in its earliest moments, when physics may have followed rules we barely glimpse today. During those first fractions of a second after the Big Bang, space-time was a dense, turbulent foam of energy and quantum fluctuations, conditions wild enough to spawn oddities like cosmic strings or primordial wormholes. In some cosmological models, those fluctuations might have briefly pinched tiny handles into the fabric of reality, linking random points before snapping shut again. These so-called quantum wormholes would still flicker in and out of existence at Planck scales even now, a part of the endless boil of vacuum energy that underlies the universe. Unfortunately, microscopic here means really microscopic, around 10 to the negative 35 meters, which is to an atom what an atom is to a galaxy, and they are almost certainly transient. They would snap shut faster than light can traverse a single wavelength. To make one large enough for even a proton to pass through, let alone a spaceship, you would need to expand that tunnel billions of times, or somehow preventing it from collapsing under its own gravity. Not easy when the universe's favorite hobby is crushing things. Of course, there is some hope, since in spite of gravity being a strictly attractive force, unlike the other three, the universe's other hobby is perpetually expanding and possibly at an accelerating rate. Early cosmic inflation, Hubble expansion, and dark energy give some wiggle room to consider expanding quantum-scale wormholes into something we could use, maybe even bigger than a proton. And from a realistic perspective, that's too small even for laser communication, as that would need a gamma-ray laser, which we probably cannot make for such a short wavelength. Even an atom-sized one is still X-rays, but you can make a wormhole you need a signal through much more easily than people and cargo. And besides the fact that FTL signaling is insanely useful in its own right, and might allow unified galactic empires, where you can send info you can send people, via brain scan, or useful personalities like an advanced chatbot with directives to load into an android or bio-droid. Back to the natural ones. Some researchers have speculated that certain black holes might secretly be wormholes in disguise, specifically the rotating or Kerr type, whose intense spin could open a passage for a fraction of a second. Others suggest that the white hole, the mathematical mirror image of a black hole that spews matter instead of swallowing it, might mark the other end of such a bridge. The problem is that we've never observed a white hole, and every black hole we studied behaves exactly as expected, one way only. Could we ever spot a real one? Possibly, but it wouldn't be easy. A stable wormhole might mimic a black hole so well that only subtle gravitational lensing effects, odd repeating quasar images, or mismatched time delays could give it away. So far, no such anomalies have been confirmed. If wormholes exist naturally, they're either incredibly small, incredibly rare, or hidden so deep in space-time that we'll never notice them. But that doesn't stop us from wondering, and from asking whether, if nature won't make them for us, a sufficiently advanced civilization might learn how to build some of its own. What keeps a wormhole open? If wormholes exist at all, they should collapse almost instantly. Gravity's default behavior is to pull inward, and any tunnel through space-time is fighting the universe's strongest tendency to close in on itself. To keep one open, you need something that does the opposite of gravity, matter with negative energy density, what physicists sometimes call exotic matter. In normal physics, mass and energy attract. Exotic matter, at least on paper, does the reverse. Instead of pulling space together, it pushes it apart, due to kind of anti-gravitational scaffolding. Think of it like propping open a tunnel through a mountain, except your supports are not steel beams. They're made of something that repels the rock instead of holding it up. Traversable wormholes depend entirely on this sort of material. Without it, the moment anything passes through, even a single particle of cosmic microwave background radiation, your wormhole collapses. Now, we've never found negative matter or any other exotic matter types that have been proposed for doing this job, and not only is there no guarantee they exist, it's more accurate to say there's very little reason to think they might. What works in math is not the same as reality. You can have a math expression for a negative cup of water, that's fine. Trying to find an actual physical example of a negative cup of water is another story, and no, a dry sponge would not count. It isn't antimatter or dark matter, something stranger, properties that would make both look ordinary. Some theoretical examples include imaginary mass particles, tachyons, or stabilized regions of vacuum with lower than zero energy. All would violate the spirit of the old energy conditions in general relativity, but not necessarily the math itself. And since we tend to think we're living in a false vacuum anyway, see our vacuum decay episode or vacuum energy episode, there is some room for thinking negative energy could exist, at least in the context of negative to us, which may or may not count, but might let you move through some lower energy state beneath this universe, or poke a hole in it and kill us all. The only verified real-world hint that negative energy might be possible comes from something called the Casimir effect. In 1948, Dutch physicist Hendrik Casimir predicted that two uncharged metal plates, placed extremely close together in a vacuum, would experience a faint attraction. Later experiments confirmed this, and the best explanation is that quantum vacuum between the plates has slightly less energy than the vacuum outside them, a genuine negative pressure. It's not quite the same thing as negative mass, but it shows that regions of spacetime can have below zero energy density, at least briefly and on nanometer scales, and we talked about this more in our vacuum energy episode. Unfortunately, the numbers are brutal. The Casimir effect produces a force measurable only with the most delicate instruments, and scaling that to hold open a wormhole would require energy densities equivalent to a planet or star squeezed in the size of a football field. The Thorne-Ellis model estimates you need something on the order of 100 million suns worth of exotic matter for a wormhole wide enough to walk through. Think Gargantua from the film Interstellar. The visceral polyhedral version does 1 billion times better, only about a Jupiter's mass for a 1 meter throat. That's still a staggering requirement, but one most star systems could afford given the advantages. Starlifting or disassembling a gas giant for that mass, maybe as burned up and fairly low value helium, would be viable. Can we build an artificial wormhole? If nature won't build wormholes for us, then the only alternative is to make our own, and that's where the theory crossed that border into cosmic engineering. Constructing a wormhole would be less like building a bridge and more like rewriting the blueprints of space-time itself. The first challenge is creating the seed. A naturally occurring wormhole, if it exists at the quantum scale, would be absurdly small, many orders of magnitude tinier than an atom. To enlarge one, you need to inject tremendous amounts of energy or manipulate gravity directly. Some proposals suggest creating miniature black holes and bombarding them with negative energy until the singularity is replaced by a stable throat. Others imagine triggering a bubble of warped space-time, kind of metric defect in the vacuum field, and then inflating it like a balloon. Either approach demands energy densities approaching the total output of a star, and technology that can shape space rather than simply endure it. Since this is SFIA, we are very open to the idea that an entire star might be turned into a wormhole factory. That's not even particularly ambitious compared to some of the projects we've discussed. The problem with size here goes the other way, in terms of trying to concentrate all that power down to a very fast blast of energy in one spot and moment. Think the size of an atom for a nanosecond, such as those contemplated for making Kugelblitz black holes, and unsurprisingly, we've got an episode deep diving that too. A few more adventurous ideas involve capturing existing micro wormholes. If the early universe did produce a sea of quantum tunnels, then perhaps a future civilization could detect and trap one before it collapses. The odds are infinitesimal, but so were the odds of catching neutrinos a century ago, and today we do that routinely. Kinda. Once caught, such a wormhole could, in theory, be expanded by carefully feeding it energy, while surrounding it with exotic matter to keep its geometry from folding back in. At larger scales, engineers would need something like a metric scaffold, a megastructure designed to contain and stabilize the intense curvature around the wormhole's mouth. Imagine a stellar-scale ring of superconducting magnets or quantum field generators arranged to balance the gravitational forces trying to tear the throat apart. In Vistor's polyhedral model, these struts might even be filled with exotic energy itself, forming a geometric lattice that holds open a sphere of space where normal geometry ceases to make sense. Then comes control. A traversable wormhole must be anchored, or else the enormous stresses of gravity and expansion would send its mouth drifting out through space like unmoored buoys on an ocean. The two ends would need to be synchronized through constant communication, possibly using the wormhole itself for feedback to stabilize its own geometry, kind of space-time autopilot. As to where they emerge, probably at random anywhere in the universe. There's some scenarios where the other mouth might emerge nearby, and then be draggable by magnetic fields and normal physics to an eventual destination. Though once you start giving one end of a wormhole relativistic motion compared to the other, you've got other issues with time travel to worry about. And which might destabilize it too, so probably either tow one slower or you move both the same speed to two eventual destinations. More likely, you don't get a choice where the other entrance emerges, it's probably random, and chances are it's so far away that light from it would never reach us. In fact, primordial wormholes would almost certainly open outside our observable universe, making it impossible to tell where you were in relation to anything familiar. Newly created ones wouldn't need to be causally linked to us either, so their far ends might lie beyond our Hubble volume altogether. That has its upsides. No need to worry about interfering with local space. No time travel worries, but it also means no nearby stars or sister colonies to visit. In effect, you'd be stepping into an entirely new universe, and if that wormhole ever destabilized, well, goodbye. You're on your own, in some galaxy far, far away. That isolation has some fascinating consequences for a civilization hoping to build a stable wormhole network, which we'll be exploring later. How would you travel through one? Let's imagine that our stableway is finished, that the immense energies have been tamed, the mouths anchored, and the geometry stabilized. What would it actually feel like to make the crossing? First, it's not a step-in, pop-out sort of trip. A wormhole has a real length, a thread of warped spacetime that may stretch from kilometers to thousands of kilometers depending on its design. Transit time depends on that internal distance, not the light years between the mouths. For a human-scale, absurdly benign visceral wormhole, the journey might take seconds or minutes of subjective time, while for a massive Thornellus gateway near a black hole galactic core, that same passage could correspond to centuries or millennia in the outside universe. Inside, time slows under enormous curvature, so travel could spend only moments crossing while eons flow beyond the horizon. Within the throat, you would not see stars rushing past or tunnels of colored light, Hollywood flare-ups aside. Instead, the geometry would distort everything. Light entering the mouth would bend and twist, forming reflections of the exit and ghost images of the region behind you. Tidal forces would vary dramatically. In the larger models, they might be gentle enough to tolerate without protective fields. In smaller or poorly tuned ones, the gradients could stretch and compress you in microseconds. A functioning stableway would need powerful inertial compensation systems, or simply be enormous enough that gravity differences across the ship are trivial. Again, this favors communication being easier and more abundant, as bigger ones for personal travel would be much harder and thus presumably rarer. Navigation would rely on precise synchronization between the mouths. Any misalignment of rotational velocity could send travelers exiting the far end with the wrong momentum, perhaps at kilometers per second relative to the destination world. To manage that, each mouth would likely be surrounded by a station that monitors space-time drift and handles traffic scheduling, and internal air traffic control for cosmic highways. Drones full of rocket fuel may be on standby waiting to snap into action to attach and help the ship change trajectory. Unstated there is that you probably don't want to be carrying fuel on any of these ships of note because you'd be better off refueling at the station on the other side, and that means less mass having to go through the wormhole. And then there's the question of time travel. Move one mouth at relativistic speed and its clock falls behind the others. A 100 light-year trip made at just under 87% of light speed would make that trip with time running at about half of normal, meaning your journey takes 116 years and you get a 58-year time deficit. You left in the year 3000 and arrived in the year 3116, but your own clock says it's 3058, and everyone jumping through the wormhole gets that same deficit. But that's actually fine. No paradox occurs, because it will still take a century for a single person to get home to screw around with cause and effect. You jump from Earth to there in 3200 AD, and it says 3142 when you get out, but the radio from home is still from 3100, so you are providing them info they can't normally yet get, but not violating causality. Now let's say some centuries later we take another wormhole made there and drag it back to Earth. Now I've got two wormholes, each with the same time deficit. This is not cancelling out though. You jump in at Earth in 4000 AD, emerge in 3942 AD at the destination, then jump through the other wormhole back to Earth and arrive in 3884, 116 years before you left. This is allowed, and you can get the same effect by dragging the original wormhole mouth back home too. And the only limit is that you can't emerge before the full system was built. No time travel before your time machine was invented. Note that a default wormhole created this mouth at some random destination in the universe probably circumvents this problem, as just about all the observable universe, and certainly all the rest of it, which I think is probably orders of magnitude bigger, is too far away for any spaceship, let alone when trying to drag entire solar masses worth of wormhole to ever return from. It's easy to forget when contemplating relativistic motion on a wormhole mouth just how massive this object is, too. You're planning to try to move it at near light speed, and it weighs as much as planets or entire stars. So the reality is that it's very unlikely you could even have this problem happen, even if you could make wormholes, and even then, only that special case of where the wormhole mouths emerge with close proximity to each other, which involves a lot more handwaves for the sake of sci-fi than actual physics. And even then, most physicists suspect nature prevents this time travel case with what's called chronology protection, where any attempt to form such a loop destabilizes the wormhole. So despite all the science fiction allure, a real stableway would probably let you cross galaxies, but not cheat time. Personally, although I doubt it could ever work, I tend to suspect a big network of these would reach some sort of temporal equilibrium, which might look really weird from the outside, assuming it didn't become an effective event horizon and go all dark to the outside. You effectively become a pocket universe. So where are we? But for the most likely case, where we find some existing primordial wormhole and grow it, or make one, you probably do the absolute minimum investment to get something maybe only a few millimeters across, enough for a tiny probe with a tiny battery to take some pictures and message home. And again, it's ridiculously unlikely you'd be able to spot anything familiar, even quasars you might share from billions of light years away, and even more unlikely you'd emerge near a star, let alone a planet. And you also want to measure the cosmic microwave background radiation to see if it's remotely the same as home, which will tell you if you're at least in the same universe and era. Not that it necessarily matters, but if you see only emptiness all around you, which will probably be the case a lot, then you collapse that wormhole and recycle your exotic matter if possible and try over. Maybe it's so easy to do that you can try over and over to get ones in the inner solar system of nice G-type stars. Maybe it's hard enough that just getting one inside some galaxy is considered great, and you send through the next wave. I do not think this involves a manned mission at this time, neither is the idea of a one-man pod a meter across might be. I think you're sending through robot constructors and von Neumann probes. Then ideally get your expansion mass locally, because bigger wormholes scale horribly. A black hole's radius is linear to mass, making it twice as massive, and the event horizon is twice as wide. But traversable wormholes under the Morris-Thorne model rise at more like the cube of mass, and the Wissel model is more like the square. So one you can get a millimeter-wide probe through, and one you can get a meter-wide pod through, are differing by a factor of 1,000 radius and 1,000,000 to 1,000,000,000 in mass. And you can repeat that if you want some kilometer-wide ship going through, and by the way, this is a 3D measurement. You cannot send a ship a mile long and a meter wide through, unless the wormhole throat is a mile wide, not a meter. And again, the more optimistic Wissel wormhole requires a Jupiter mass worth of negative matter or energy to exist, so even a millimeter-wide probe wormhole is taking a large asteroid to make. Even a micrometer scale one that you could just barely get a visible laser through is in the Mount Everest mass zone of exotic matter. You might even be able to do some astronomy through this, but your wormhole has to be at least as big as the wavelength of light you want to look at, and the CMB is a millimeter, while radio is even longer. For sci-fi purposes, and for anyone watching this with that in mind, I'd really handwave some reason why a meter-wide one was your minimum. That makes it sane to send people through, and telescopes that might rival Webb or Hubble, and make the storyline easier to write. But it's not, so you send your probes out to build telescopes, and find something they can harvest for mass to build bigger telescopes, and on the early ones I think you are making a big effort to pin down the CMB temperature and locate neutron stars and quasars. If the cosmic microwave background radiation, CMB temperature, is off, then you're in a different time or universe. If you can't find any neutron stars you recognize, then you're not in our galaxy or a close neighbor. But if you did, you could actually get a real position down pretty quick, in astronomer terms anyway. There's no popping a ship through one, the captain balking, "Report, helmsman, where are we?" It's, "Get the telescopes extended and tell Astronavigation Department I want an answer by the end of the month." And faster computers are not really helping with this. If those neutron stars are a no-go, your next bet is quasars, and at this point you are effectively signing off on ever getting a message home if that wormhole snaps shut behind you. Because even if you find some shared quasars, the distances involved are at the hundreds of millions to tens of billions of light years. Might get some awesome new astronomy done though if you did, and I would be curious what the average and median distances of new wormholes worked out to be, or the frequency of created ones that could see a shared quasar. If the CMB is all different, which is probably the fastest to detect, then you might also be wanting to check what the local speed of light is, and the other physical constants. They might be different too, and indeed might favor easier wormhole creation or growth. But ultimately, whether or not this is in another universe or some distant chunk of it so far away it might as well be, it is great for colonization, either by sending people through, if you can, or self-replicating machines that build stuff and grow people, or biodroids for mind uploads. Civilization across the Stableways. If wormholes could ever be made stable and scalable, they would redefine civilization itself. A working network of Stableways would be to space travel what the internet was to communication, or what the invention of writing was to memory. Once you can move people, goods, and energy through permanent shortcuts in spacetime, the speed of light stops being the barrier that defines our universe. The simplest form of network might start modestly, a few communication-scale wormholes linking distant outposts or research colonies. Even a throat just millimeters wide would let you exchange data faster than your radio signal. Even this, if it is as big as we can go, allows us to remain connected. Though if wormhole is truly placed randomly, I think you end up with Earth connected to hundreds, if not thousands, of spacefaring empires you could speak to the capitals of in under a day, but which themselves might soon suffer the same problems a no-FTL interstellar empire has as they expand out from that wormhole, or perhaps create their own network of wormholes around them like Earth did, all extending out to random places in the universe. If we could get bigger mouths, over time these could grow or be replaced by transport-sized gateways, meter or kilometer-wide throats big enough for ships, cargo pods, or even entire habitats. Soon you have an hierarchy of routes, local hubs for star systems, regional trunks linking sectors, and colossal intergalactic junctions where multiple Stableways converge. From our earlier Stargates episode, we might imagine a hub-and-spoke design, with carefully scheduled activations to manage power and traffic, rather than a chaotic open network. And it applies here too, so see that episode for some examples of how this scales. Economically, the implications are staggering. Interstellar trade ceases to be a matter of centuries and becomes a matter of minutes. Of course, with that kind of power comes both risk and politics. Wormholes will be the ultimate strategic choke points. Whoever controls the gate controls the galaxy. They are also probably relatively easy to collapse compared to building one, probably not super sensitive so that any terrorist or raid could wreck one, but very much a case where you need to defend it. Armies and navies might shrink in importance compared to whoever holds the passwords, or the exotic matter chain supply. A collapsed throat could isolate whole sectors overnight and forever. Civilizations might sign non-collapse treaties, ban the use of wormhole destabilization as a weapon, or agree on shared defense protocols to prevent anyone from simply detonating a gate and taking a star system with them. And again, they're fairly massive, so it's quite possible the star system does actually orbit the wormhole. Given enough time, if wormholes are easy to make, then you might have to populate the entire universe before you could expect to get wormholes to existing systems. You probably could make that happen in relatively short order. A trillion stars, each with its own Dyson swarm worth of people, is still only about 35 doublings of our population. And at our current growth rate, rather slow compared to the last century, we still get there in under 4,000 years. Probably way slower considering the workload involved, but even then, if it took 100 times longer, what's 500,000 years at the cosmic scale? At that point you're starting to pop open new wormholes from here at our colonies where often it's already a colonized star system, and where neighboring systems you colonized a long way are popping up their own forced wormhole to already inhabited systems, albeit most often on the other side of the universe. Statistically, if you have 10 wormholes per system, you can get most places in the known universe in a couple dozen hops. If you had 100 wormholes per system, then more like a dozen hops. And even 1,000 gates per system only lowers that to 8 hops, so your sweet spot is probably in the 10 to 100 range, and probably would be the difference between major hub worlds, a minor one, and some place like Earth, which might have harvested whole star systems to give itself thousands of wormholes in system. Given the jump to random spot nature of them, you are also vastly more likely to see traces of other civilizations engaging in the same expansion than you would by sublight expansion or even traditional warp speed FTL. Alien wormholes opening your own settled space are relatively unlikely, but obviously a cause for concern too. They are very vulnerable to early attack. You can't just pump an armada through a brand new one, but one opened up is most likely arriving in very deep space, light years from a star, and presumably your space armadas, which are probably not built around interstellar flight either. That's a lot of time for someone to fortify before you spot them, a couple years of light lag at least, and can do anything about it. So alien beachheads are a real concern, and feel free to steal that for a story. And again, there's no reason these would be limited to our observable universe, and for all we know the wider universe is infinite, and these might be going to other universes too, which would scale things up even more. Our Cosmic Capitals episode tries to contemplate that scale, as did the Stargate episode. But if you've opened a billion wormholes and never had one even land in the same identifiable galactic cluster, then you have to start contemplating reality might be a lot bigger than we ever dreamed. And through it all, the maintenance never ends. Wormholes would require constant stabilization, energy inputs, and field monitoring. Invasions through them are not realistic, so you need to control both sides and have ultra-loyal and heavily defended star fortresses and armadas there, as even sending reinforcements in a reasonable time window is likely to be difficult. David Weber contemplates that throughput issue of wormholes in one of his Otterverse novels. Wormholes definitely have maximum throughput limitations, even if the specifics are hard to nail down. Each would be a living piece of infrastructure, like a star-sized organism that must be fed and tended lest it decay. The Stableway network might become the largest collaborative project in the history of intelligence, an empire not built on conquest but on geometry, uniting its builders across time and space. The key point about wormholes is that any naturally occurring one is probably a time portal too. Paradoxes aside, that opens up some fascinating possibilities, like being able to see Earth in its primordial days. But you don't need a wormhole for that. Just watch Joe Scott's Nebula documentary, Oldest and Newest Places on Earth, where he travels from some of the oldest exposed rock on the planet to lava that's literally rewriting the map of Hawaii. Many of you already know Joe's work, so you know it's worth watching. He and I have collaborated on a lot of projects over the years, including Nebula, the largest creator-owned streaming service, home to original, thought-provoking content from us and many other great creators. It's also where every episode of SFIA premieres early and ad-free, along with monthly exclusives like The Future of Interstellar Communication, where we explore how civilizations might stay in touch across light years without wormholes allowing fast conversations. Nebula is where I release a new exclusive episode like this every month, along with bonus content and extended editions. Use my link or the QR code on the screen to get 50% off an annual plan, just $30 for the whole year, about $2.50 a month. Head to go.nebula.tv/IsaacArthur and start watching today. Bridges to Eternity. A functioning network of wormholes would be far more than a transportation system. It would be the nervous system of the civilization itself. Once established, it could last far longer than empires or species that built it. Plants and people would come and go, but the Stableways would remain, humming quietly in the dark, carrying energy, data, and perhaps even life itself across the stars. It's easy to imagine such a network sprawling beyond our galaxy. Supermassive black holes at the hearts of galaxies might make perfect anchors, their immense gravity providing both stability and power. If even a few ancient civilizations learned how to use them as hubs, the Milky Way could be just one node in a greater galactic web, with billions of connections arcing invisibly through intergalactic space. To an observer in the void, nothing would seem unusual. No bright beams, no starships flashing past. But through unseen corridors, civilizations might trade knowledge, art, and memories faster than light, bypassing the slow crawl of normal space entirely. If such networks exist, that could help explain the Fermi paradox, why the galaxy appears silent. Perhaps the neighbors are talking but not through any channel we detect. A wormhole civilization wouldn't need radios or lasers. Its traffic would be hidden within its own geometry. We might be surrounded by an interstellar internet that doesn't use space as we know it. They also might be opening to places far more interesting to settle than our own universe. So people go there, not elsewhere in our own universe. You might migrate to a better universe or find one that's more energetic to run your power plants. Maybe there could be engines for starships, or for that matter, bridges to eternity. In the far future when the suns have burned out, and the universe cools toward heat death, wormholes might remain the only means of communication or travel left. Civilizations could huddle near the last stable gates, pulling their remaining energy to maintain the links. Even as the cosmic background cools and entropy wins, information might still flow, an echo of life defying the silence. Wormholes could be the last infrastructure in existence, not just spanning space but time itself, connecting the dying embers of one cosmos to the birth of another. We often talk about Dyson spheres as monuments of civilization, but Stableways would be something more profound. Monuments of connection. They would tie galaxies, epochs, and even universes together into a single vast continuum. To maintain such a network would be to hold the threads of reality itself, to ensure that no matter how far the night stretches, there's always a bridge back to somewhere. And perhaps that's the truest legacy of any intelligent species. Not how many stars it claims or how long it endures, but how far it can reach out and connect. For all our talk of colonizing space, it may be that our greatest work will not be the worlds we build, but the pathways we forge between them. The stableways that let thought and life cross the distances between galaxies and ages. From quantum foam to cosmic highways, wormholes remain among the most audacious ideas in all of physics, equal parts dream and danger, calculation and fate. Whether they are ever built by human hands or only by the equations that allow them, they remind us that space is not an empty void, but a canvas waiting for civilization to draw its connections across it. If space is an ocean, then wormholes are not the sails of the ships, they are the harbors between the stars, and the day we build them, humanity will no longer just cross the cosmos, we will bind it together.